Have you ever been staring at a coding interview problem and it just feels impossible? Well, what if I told you there's a secret weapon that turns those absolute brain busters into pretty straightforward exercises? That weapon is dynamic programming. And, over the next few minutes, we're going to pull back the curtain and demystify it so you can walk into your next interview and just nail it.
So, you've definitely seen something like this before, right? A super simple recursive function, maybe to calculate a Fibonacci number. You write it, you run it for a small number like 10, and boom, it's instant. But then you get brave. You try it with, say, 100, and your computer just freezes up. The fan starts screaming, and it's just thinking. But what is it actually doing?
It's doing this many operations. Yeah, that number is over 10 to the power of 20. To give you some perspective, that's way more operations than there are grains of sand on every single beach on planet Earth. It's an absolute nightmare of exponential growth, and it's exactly the kind of problem dynamic programming was invented to crush.
So what's the deal? The whole problem boils down to one simple, fatal flaw: redundant work. We are solving the exact same problems over and over and over again. Think about it. To get the fifth Fibonacci number, you need the third. Then to get the fourth, you need to calculate the third again. All this wasteful repetition is what causes that insane exponential explosion. And this is where DP just swoops in to save the day. It's this incredibly powerful technique that takes these impossibly slow problems and makes them totally efficient, all by doing one simple thing: remembering the answers to problems we've already solved. It's basically like giving your code a cheat sheet. Okay, so let's get into it. How does this magic actually work? Well, the entire concept of dynamic programming really just boils down to looking for two key ingredients in a problem. If you spot both of these, it's a huge sign that DP is probably the way to go. Ingredient number one is something called optimal substructure. It sounds fancy, but all it really means is that to find the best overall solution, you first have to find the best solutions for all its smaller parts. Imagine you're building something with Legos. To build the best, most awesome car, you first need to build the best possible wheels, right? And the best possible chassis. The big, optimal solution is just built from smaller, optimal solutions. And the second ingredient is overlapping subproblems. And this is exactly the mess we just saw with Fibonacci. It's when a simple recursive approach ends up solving the exact same tiny problems again and again. Dynamic programming is what spots this pattern and basically says, whoa, hold on, I've already solved this. I'm not doing all that work a second time.
And that right there brings us to the core philosophy, the entire soul of DP. Solve each little subproblem just one time, and then save that answer, store it somewhere. Because the next time you need it, you just look it up. No recalculating necessary. That's the whole game.
So now that we get the why, avoiding all that repeated work, let's get our hands dirty with the how. The most common way to actually build a DP solution is with a method called tabulation. And that's just a fancy word for building a table of our answers from the ground up, starting with the absolute simplest cases. And you can think of it like a reliable 4-step recipe you can follow every time. First, you define your state. What does each little box in your table actually represent? Second, you initialize your base cases. These are the answers to the simplest possible versions of your problem. Third, and this is the big one, you find the recurrence. That's the rule that lets you build bigger solutions from the smaller ones you've already found. And finally, you figure out where in your finished table your final answer is hiding. All right, enough theory, let's make this real. We're going to take our recipe and apply it to a classic problem called edit distance. It's the perfect way to see 2D dynamic programming in action. So here's the problem. I give you two words, like kitten and sitting. What's the absolute minimum number of edits? And by edits, I mean insertions, deletions, or replacements to change the first word into the second. And this isn't just some abstract puzzle, This is the core logic behind everything from your phone's autocorrect to how scientists literally compare strands of DNA. We start by setting up a simple grid. The rows can be for prefixes of kitten and the columns for prefixes of sitting. Okay, so what about our base cases? Step 2 of the recipe. Well, what's the cost to turn an empty string into sit? That's 3 insertions, easy. And the cost to turn kid into an empty string, 3 deletions. So we just go ahead and fill that first row and column with these simple costs. And just like that, step 2 is done. Now for the fun part, the recurrence, the rule that's going to build our whole solution. To figure out the value for any cell in the grid, we just have to look at its 3 neighbors. We can get here from the cell to the left, which would be like an insertion. We could come from the cell above, which is like a deletion, or we can come from the diagonal, which represents a replacement. All we do is ask, what's the cheapest of those 3 options? We take that minimum value, and that becomes the answer for our current cell. And when we do that, we get this beautiful result. We just apply that one simple rule, cell by cell, filling the table from the top left all the way to the bottom right. Each new cell is built on the already solved optimal answers of its smaller neighbors. And by the time we get to that bottom right corner, there it is, the final answer. The minimum edit distance to get from kitten to sitting is 3.
The real beauty here is just how efficient this is. A naive recursive solution would be terrifyingly exponential. But with our DP table, the solution is just O of n times m time. And while this version takes O of n times m space, you can actually get even cleverer. Since you really only need the previous row to calculate the current one, you can optimize the space all the way down to O of the minimum of n or m. Pretty cool, huh?
So, let's bring it all home. Why does any of this actually matter? Well, because DP problems show up in technical interviews all the time, and really understanding this pattern can be the thing that separates a yes from a no thanks. So let's cover some crucial tips.
Okay, a really common interview trap is confusing DP with greedy algorithms. Here's an analogy. Imagine you're climbing a mountain. A greedy approach is to always take the steepest path directly in front of you, just hoping that's the fastest way to the top. But you could easily end up on a smaller, fake peak, not the true summit. DP, on the other hand, is like having a detailed map of the entire mountain range. It patiently explores all the paths from the bottom up, guaranteeing you find the absolute highest point. So use greedy when you're sure the local best choice is always the global best choice. But use DP when you absolutely have to find the guaranteed optimal solution.
Here it is, your interview cheat sheet. Number 1. Before you do anything, clearly state what your DP table represents. What does DPIJ mean in plain English? 2. Get your base cases right. If they're wrong, literally everything that follows will be wrong. 3. Figure out the transition logic on a whiteboard before you type a single character of code. And 4. Code it bottom up. And seriously, please double-check your array indexes. That's where like 90% of all DP bugs come from.
So if you remember one thing, let it be this. Don't just jump into coding. The real solution isn't in the code itself, it's in the logic behind it. If you can clearly explain your state, your base cases, and that recurrence relation, writing the code becomes the easy part.
Look, dynamic programming isn't about memorizing a bunch of solutions. It's about learning to recognize a pattern. It's a pattern of breaking huge, scary problems down into smaller, bite-sized, reusable pieces. So I'll leave you with a challenge to really take what you've learned today and run with it. How would you use these same ideas, maybe with just a simple 1D array, to solve the coin change problem? Find the minimum number of coins to make a certain amount. Give it a shot. That's how you really start to master the stuff.